You are at the public swimming pool and you're brave enough to go up the diving board and then you jump. You accelerate, fall and splash. Then you measure the height above ground over time and you know it has to be parabolar, so proportional to t squared. But why? Couldn't it be something else? Why is proportional to t squared the correct solution? Welcome to this video where we will use functionals and functional derivatives to show that this is the correct solution. Hi! The agenda for this video is that I will first give an intuition to functionals, then we will play around with them a little bit, and in the end we will do functional derivatives in order to minimize the functional, and then we will see that the solution that we're getting out or that we conjectured is actually the correct solution. And if you look at the problem of our diver jumping into the water, you could of course say that this is solvable by Newtonian mechanics, so it's also solvable by Newtonian mechanics. And Newtonian mechanics is just complicated for saying that we use the classical F equals m times a and then solve the ordinary differential equations. But that's not what we're doing here. Not here, but anyways, still we will see that later on in the video, this equation naturally arises from the approach that we will be using. And our approach is based on the idea of energy somehow conservation. It's a little loose, but let's think of it like this. So let's define the energy that our diver has. So when he starts, he is on our diving board, then he jumps up, and we are looking at him. Once a point, he reaches the top of his curve, and then he's falling straight down, just for simplicity. And we are considering two types of energy. We have the potential energy, and the potential energy is m times g times h, and the kinetic energy is 1/2 mv squared. And in here we have the following constants. So m is the mass of let's call him the diver, and g is the acceleration due to gravity. And then we have h, which will be the height above ground, and he will start at a certain height and then he fall down. And v will be the velocity that he has at a certain point in time. And we can of course express these two quantities by the help of our coordinate y that we introduced. And we can say, well, h is nothing else than y, and v is nothing else than y prime or y dot, which is the temporal derivative. So this is nothing else than dy by dt. And then we get m times g times y. And for the kinetic energy, we will get 1/2 m y dot squared. So now let us make some simplifying assumptions, because we now have some constants for physics, but we are more interested in the mathematical sense. So let's give them some simple values. So let's say if m is 2 kilogram and g is 2 meters per second squared, and we will see in a second why we choose them. See later why. And they will become quite natural. And if we do this, then our height above ground and our time when we will splash into the water will both be 1, as we already had it here on the axis of our coordinate system. So let's say then if the height is 1 meter, then the time of splashing will be 1 second. So we will have 1 second of air time, you could call it like this. And then we get the following. So we have then a kinetic energy, and it is y prime squared, because we plug in the 2, then the 2 cancels, we ignore the units, and then we get y prime squared. And for the potential energy, we will get, well, we plug in 2 and we plug in another 2, then we get 4 times y. And now let us introduce something that might seem a little odd at first. And we will do the following. We will do the integral from 0 to 1 over the time. And so this is the time when we are in air. And in this integral, and inside this integral, we will be subtracting the potential energy from the kinetic energy. And in case you've seen this before, this is Lagrangian mechanics. I mean, it's not necessarily relevant for the sake of our argument here, but I just wanted to give the link and in case you've heard it. Okay, let's plug in what we had. in our case, we would get the integral from 0 to 1, and the kinetic energy is y prime squared, and the potential energy is 4 times y, so y prime squared minus 4 times y dt. And of course, recall y is a function of t, so also y prime is a function of t, so the integration over t in a sense makes sense here, because we will plug in our function that is describing the height over time. And now let's give this integral a name, and we will call this a capital I, and this capital I depends on y. So we plug in a function y, and then we get out a value I. But what is this value I? Well, there is like a loose interpretation for this, and I will also frame this loose here, and it is that is the average difference in energy. Okay, this seems a little strange, but you know, you take the difference of these two energies and then you integrate, so it's some sort of an average. But that's technically wrong because it's not an energy, so we can also not think of it as a difference, but it is necessary to kind of ensure feasibility. And we will see in a second why this is the case. So it ensures feasibility. And let's be a little bit more verbose. So I is something that takes in a function y and outputs a scalar, because the integration, well, then we don't have a function anymore, and it will just be a scalar value like this average difference in energy, and that is called a functional. And we call it a functional because, loosely speaking, it's a function of functions. Because, you know, the function y associates each time with a height above ground. So you plug in a scalar value, you get out a scalar value, and now we have a function that takes in a function and outputs a scalar value, a functional. And let's give it a little bit context. Let's try to plug in some functions. So let's try to calculate the value of the functional for y being 1 minus t. So let's go back up. In our case, we would expect the true solution to be 1 minus t squared, but let's assume now that we have a solution that is just a straight line. I mean, it could also be some sort of a proposal. And let's try to plug this in. So then we get the integral from 0 to 1 over 1 minus t in brackets prime squared minus 4 times 1 minus t dt. Then the integral from 0 to 1. So let's first take the derivative. 1 minus t with respect to t will be minus 1 in brackets squared minus 4 plus 4t dt. And then we get the integral from 0 to 1. Minus 1 squared will be 1, and 1 minus 4 will be minus 3 plus 4t dt. Then we build the antiderivative, which will be minus 3t plus 2t squared, and we evaluate at the limits 0 and 1, and then we plug in minus 3 times 1 plus 2, and we can ignore the lower bound, so we're getting minus 3 plus 2, and this is minus 1. And you already see this is a negative value, so it's some sort of like average difference in energy. I think you get it's like a loose interpretation, but bear with me. Okay, let's plug in another value, and let's plug in the solution that we expect, which is y is 1 minus t squared. So the integral from 0 to 1 over 1 minus t squared in brackets, take the derivative square, minus 4 times 1 minus t squared in brackets dt. And then let's first take the derivative, which will be minus 2t in brackets squared, minus 4 plus 4t squared dt. Then let's evaluate the square, and we're getting 4t squared minus 4 plus 4t squared, which makes 8t squared minus 4 dt. Then let's take the antiderivative. In this case, it would be 8 over 3 t to the power of 3 minus 4t, evaluated from 0 to 1. Ignore the lower bound at 0, so it will be 0. And we plug in 1, so we get 8 over 3 minus 4. And in this case, we will get minus 4 over 3. And this is approximately minus 1.333. And then let's go on. Let's plug in another solution. This is also a possible proposal. You do 1 minus t to the power of 3. And the integral 0 to 1, 1 minus t to the power of 3 in brackets, take the derivative, square it, minus 4 times 1 minus t to the power of 3 dt. Okay, keep the integral, then take the derivative, which will be minus 3t squared. Then we square this, minus 4 plus 4t to the power of 3 dt. Then we get the integral from 0 to 1, and we have 9t to the power of 4 minus 4 plus 4t to the power of 3 dt. Build the antiderivative. Here we will get 9 over 5 t to the power of 5 minus 4t plus, and here we will get just t to the power of 4 from 0 to 1. Then let's plug in our bounds, and we get 9 over 5 minus 4 plus 1. So we get 9 minus 20 plus 5 over 5. This will be 9 plus 5 is 14, minus 20 will be minus 6 over 5, and this is minus 1.2. Okay, well, this was tedious, surely, but now let's compare the values once again. And for the one solution, for 1 minus t, we are getting minus 1. For 1 minus t squared, we are getting minus 1.33. And here we're getting minus 1.2. Let's note this down. So the I value, or the functional for y is 1 minus t, was minus 1. And the functional for y is 1 minus t squared was minus 1.33. And the function of y minus t to the power of 3 was minus 1.2. And if you look at this, then you see that's the minimum. I mean, it's the minimum of the 3 values that we calculated, but that's kind of suspicious, isn't it? And we know it's associated with the correct solution. We know the correct solution must be this, and it has the minimum. Maybe this reminds you of the minimum energy principle. Let's look at this a little more visually. So here we have a plot with the height above ground being starting at 1, and we splash into the water at the time being 1, and then we have a function proposal, in our case 1 minus t to the power of 1, and recall we calculated the value to be minus 1. And now I can adjust the slider here and change the exponent, and so we slowly go up to 1 minus t squared, and then we get our minus 1.33. And then we go up to 1 minus t to the power of 3, and we get minus 1.2, and we can go on, and we see. And if we play around with it, then you might notice that this integral takes its minimum value at the true solution. And I think this I hope this visual approach kind of gives a little more sense to what we have with this average deviation in energy. Because actually we encoded a really natural principle that our solution must minimize this average deviation in energy. So before we go on with this idea of the minimum energy principle, let's be a little more explicit and answer the question, what is a functional? And we saw that the functional is a function of function. This makes sense, but let's be a little more mathematic. So y was a function from the real numbers to the real numbers. I mean, it makes sense. So we plug in the time, which can be a real value, and we get out a height above ground, which can be a real value. But now our I, or the average deviation of energy, was that something with an input from a function space, and it was mapping it to the real numbers. So it was outputting like this scalar value. Let's be a little more explicit. So these are scalars, and these are also scalar values. And examples for function spaces are first the infinitely often continuously differentiable functions. Well, this is a mouthful. And these functions are given as follows. So we define, or we would write down something as C and upper index infinity over RR, because the functions itself, they are mappings from real values to real values. And this is just one way to, or one function space. And also we have the square integrable functions, also a mouthful, and we denote them as L index 2 over RR, because they also have like an input and an output space. And of course, probably the more easier example would be the space of polynomials, which is probably more approachable than the two others. Okay, but going back to our suspicion that we have a minimum energy principle, and this could then bring up kind of like the conjecture, the true solution is attained at minimum energy. Well, I mean, this makes sense. So nature is trying to reach a minimum energy state. And this then raises the question how to minimize a functional. And of course, I mean, a good approach would be what we would also know from our function is to build derivative and set to 0. And this is actually the correct way of doing it. But this then brings up the next question, like how to do a derivative. And I mean, of course, this is not a trivial question because we don't have real values here. I mean, this is not technically what we know about differentiation, but it's the approach that we will be doing. And so keep this in mind. This will be the reference for what we will be doing in the next step. Okay, let's call this the functional derivative. And for this, we will denote it as following and say we use a delta of our functional and we derive with respect to y. So we derive with respect to a function. Of course, but how should we do this? And for this, let us look at the following. So let's say this is the space, the function space that we are considering. I mean, I don't want to use a particular example, just think it as a function space. And usually this function space is infinite dimensional. So if you were to draw a coordinate system, then it would have like infinitely many axes and it would be really cluttering. So let's also note this down. This is an infinite dimensional and correctly would be vector space. And inside the soup, we will also find our function, or the true solution was 1 minus t squared. And we can now move alongside a function in this function space. So for instance, let's say we have kind of this direction and we kind of see a function in here and it will be like a vector. And this function is given as t squared minus t to the power of 3. And if you would add up these two values, then we will get a new function, which is 1 minus t to the power of 3. And we know this is no longer a solution. So we also know that this is the minimum. I mean, we don't know it yet, but we will see in a second. And what we can now do is similar to what we also would be using to define a derivative for scalar value functions. We can move a little bit alongside this direction, and we call this little bit an epsilon, and then we evaluate the solution once here, and then take the difference and let epsilon slowly move towards 0 so that we only have the actual solution and we get the derivative. Okay, this might be a little confusing, but let's put this into mathematics. So we have a functional and we want to derive it with respect to the function y. Then this is given as the classical derivative of the function evaluated at y plus epsilon phi with respect to epsilon at epsilon being 0. So we move alongside the phi function and then we show what is the slope of this alongside this function and we set epsilon to 0. And this is nothing else as a directional derivative in function space. And in mathematics, there would be also like a more explicit name for it, and there it is called a so-called Gateau derivative. But for the sake of simplicity, we will just call it functional derivative. But well then, so we know how to take the derivative, then just do the derivative of the functional with respect to y and set it equal to 0, right? And then solve for y. And then we get our optimal or minimal solution. Then let's do this. Okay, let's do this step by step. And we start again with our original functional, which was I of y given as the integral from 0 to 1 over y prime squared minus 4 times y dt. And of course, recall y was a function of t, so this integral kind of integrates out the dependency on t. Then let's plug in our augmentation. So we let our value vary a little bit alongside another direction, phi. So let's plug this in. So then we have y plus epsilon phi, take the derivative, square it, minus 4 times y plus epsilon phi, and then integrate over t. Okay, let's take the derivative, and we have a summation, so we get y prime plus, and epsilon does not depend on t, so we just get epsilon phi prime and square it, minus 4 times y plus 4 times epsilon phi dt. And also let us note this down, epsilon does not depend on t. And then we can evaluate the square and get the integral from 0 to 1 over y prime square plus 2 times y prime epsilon phi prime, and then we have plus epsilon squared phi prime squared minus 4 times y plus 4 times epsilon phi dt. And truly, of course, I made a mistake here. This should be a minus. And then we can go on, and then we do the derivative, but the classical derivative of our augmented input with respect to epsilon. And since our limits of integration do not depend on epsilon, our derivative just propagates over the integral, and we can differentiate with respect to epsilon. So, well, there is no epsilon here, so this kind of vanishes. Then we get 2y prime phi prime. Then the derivative with respect to epsilon would be 2 epsilon phi prime square. And there is no epsilon here, so we get a 0, and we get minus 4 phi dt. Okay, let's make this a little more clean, and we get 2y prime phi prime plus 2 epsilon phi prime square minus 4 phi dt. And then last step, we set epsilon to 0, so we keep this, and this was the augmented input, then the derivative with respect to epsilon, and now we set epsilon to 0, and then we have the integral from 0 to 1, and then we get 2y prime phi prime, and here this vanishes because there's an epsilon inside, so we get a 0, and we have minus 4 phi dt. And this is our functional derivative of I with respect to y. Okay, great, but this is not a solution. So how do we rearrange this for y? So let's call this how to rearrange for y. And for this, we need to make some tricks. And we have to get rid of the prime over the phi in order to apply a trick from mathematics. And let's just do it, and then we will see it makes sense. So we have the integral from 0 to 1 over 2 y prime phi prime minus 4 phi dt. And we can also just split out the integral and let the first be the integral from 0 to 1 over 2 y prime phi prime dt minus the integral from 0 to 1 over 4 phi dt. And then let us apply integration by parts. So integration by parts for the first integral. And we want to integrate phi and derive or take the derivative of y. Then we get 2y prime phi evaluated at 0 and 1 minus, because this, don't forget this, integration by parts. And then we have the integral from 0 to 1 over, and here we will have 2y double prime phi dt minus the integral from 0 to 1 over 4 phi dt. And here we will use a property of the phi because, and this will be 0 at the boundaries, and this is because phi is a so-called test function. And earlier, when I gave it the example of the t squared minus t to the power of 3 is actually not fully correct. So this was just like to give you a hint on how this could work. This is a special set of functions. So this has to hold for all the phi's from a special set of functions. I don't want to discuss it further. Just believe me that they have this special property that they vanish at the boundary, and then we can go on. and get the following, and we have then the integral, or minus the integral, from 0 to 1 over 2 y double prime phi minus, and let's put the minus in front of the integral, so we get plus 4 phi dt. And now we have another property, so let's make it like this. So the integral from 0 to 1 over 2 y double prime plus 4 in brackets multiplied by phi dt. And now we know that this was nothing else than the functional derivative of our functional with respect to y, and this has to be 0, right? I mean, we want to set the first derivative to 0. And then we can apply something that is called the fundamental lemma of calculus of variation. And this essentially, so let's write this down, the calculus of variations, and this essentially tells us that if we have a test function multiplied with something inside an integral which has to hold to 0, then this is equal to the whatever is inside of the integral multiplied by phi, so in our case minus 2y double prime plus 4 is also 0 outside of the integral. So it does not hold only in the integral sense, but it also holds in the pointwise sense. And then we get the following, and we then can rearrange this for 2y double prime plus 4 is 0. And if we then rearrange this equation, we get y double prime is minus 2. And that is the condition for the optimal solution. So recall, because actually we wanted to minimize our functional, and now we found just a condition, but this makes a lot of sense. And I will now go all the way back up. We did quite a lot of stuff so far. And if you look at what we had here, I said that we can also solve this by Newtonian mechanics. And we just figured out that f is m times y double prime. And in our case, this would just be that m times g is m times y double prime. And recall, in this case, m would cancel, and we know that y double prime would be g. And g is acting in the negative y direction, so it would be minus 2. And we set it to 2. And this makes a lot of sense now, right? So if we go back down, we see that here we have a minus 2. So because g was 2. And that's fantastic, right? So we just rediscovered Newtonian mechanics. So let's call this, we rediscovered Newtonian mechanics. Well, this is just a side note. It has nothing to do necessarily with the mathematics, but it's something that I find extremely remarkable. And then this is nothing else as an ordinary differential equation, which we can solve by integration. So we integrate once and we get y prime is minus 2 times t plus y prime 0, which would be the initial velocity. And we know the initial velocity would be 0 because we measured when we were at the highest point of our jump. So instead of like starting to jump, just for simplicity, then we integrate again and we get no prime anymore. So just y, and we get, well, then minus t squared plus y0. And we know y0 was 1 because we started at the height of 1. And then y, as the function of t, is just 1 minus t squared. And with this, we found that 1 minus t squared is indeed the solution that minimizes the functional. So put this into words. So y prime of t, 1 minus t squared, is indeed the correct solution as it minimizes, and the functional that we looked at is called the energy functional. And the minimization of the energy functional, that makes a lot of sense because of the minimum energy principle. And this is a really long video on the introduction of functionals and functional derivatives. So I will just quickly recall the most important fact of our derivation. And whenever you want to do functional derivatives, then think of the Gateau variation. And the Gateau variation is given as this one here. So you take the derivative of a functional with respect to a function, and then you do this. You take the derivative of an augmented input with respect to a scalar value epsilon, and then set epsilon to 0. And this is the really important step. And if you then want to apply like the idea that you have to set the derivative to 0, then it might turn out that you have to do integration by parts. And recall, this can be a little tricky, but sometimes you have to do this. And then in the end, you can apply the fundamental lemma of calculus, and then you find equations that have to hold in order for us to have the minimum solution. And with this lengthy introduction to calculus of variations, functional derivatives, etc., I'm at the end of the video. I hope you could follow along, and also feel free to write a comment if something is unclear. I would be happy to answer that. And again, thanks for watching. Thanks for staying with me until this point. This is really tough of you, and I hope you enjoyed it. Here you will find similar videos. If you like this video, then consider subscribing and giving a thumbs up. And with this, see you next time.